Hello, my name is Mikito Nanashima. Today I'm going to talk about our work entitled Extending Learnability to Auxiliary Input Cryptographic Primitives and Meta-PAC Learning. So now let's begin with introduction. Which concepts can be learned efficiently or in polynomial time? This is a very central question in computational learning theory. And one unconditional limitation on efficient learning is the following. Any efficiently learnable class is also efficiently computable. In other words, learnable classes are contained in computable classes. Then the natural question is whether these classes are equivalent or not. But maybe many researchers believe that the left one is correct because this is implied by very standard cryptographic assumption, that is one-way function. And this gap between computation and learning is sometimes called as a LIH, learning is hard assumption. But how strong and useful is this assumption? Or what is the exact meaning of this hardness of learning? This is our main concern in this work. More specifically, the existence of one-way function implies hardness of learning, and hardness of learning implies that P not equal NP, and the other directions are currently open. In other words, the assumption learning is hard is stronger assumption than the usual assumption on P versus NP, but less useful than the cryptographic notion. Then what is the exact meaning of hardness of learning? In this paper, we consider this part and we give new two meanings of hardness of learning. The first one is weak cryptography. The second one is the difficulty of determining efficient learnability. Before explaining these results, first let me specify the learning model, PAC learning. But this model is sometimes called as a prediction model or improper learning. First of all, concept is a Boolean function, and the concept class is defined as a class of Boolean function. But in our case, this is a class of polynomial-sized circuits. In this model, learner learns a target function in the concept class and some unknown example distribution. And first, samples, which is a tuple of input and functional value, and a challenge is generated according to this example distribution, and they are passed to the learner. And the task of learner is to output to predict the functional value of this challenge with good probability in polynomial time. And in this model, this learner must learn any target function in the concept class under any example distribution. So now I explain the first topic. The first topic is about learning versus cryptography. So let me introduce several previous work. The first relationship between these two fields was given in pioneered paper by Variant, and he showed that a one-way function, which is a very fundamental cryptographic primitive, implies hardness of PAC learning. The other direction was first considered by Brown et al., and they introduced a specific learning model whose hardness corresponds to the one-way function. Later, Applebaum et al. Observed that, in fact, a weaker cryptographic notion, that is auxiliary input one-way function, is sufficient to show the hardness of PAC learning. But the other direction is currently unknown. Later, Shao introduced another learning problem called circ-learn, and he showed that this hardness of circ-learn implies auxiliary input one-way function, but the other direction is also unknown. Then, what is the exact notion in learning theory corresponding to this auxiliary input one-way function? And our first result is to give answer to this question by specific learning model called PAC learning with target sampling circuits. And we showed that this hardness of this model corresponds to auxiliary input one-way function. Now I explain this model. A model PAC learning with target sampling circuits is intermediate model between usual PAC learning and circ-learn. In usual PAC learning, first unknown target function and example distribution generates samples and a challenge, and the task is to find good prediction. And in this model, learner does not know how to generate these samples. On the other hand, in SAC-RAM, the learner is given a circuit generating a sample, and the task is to find good hypothesis with respect to samples generated by this C. And our model is intermediate model in the sense that the learner is given samples and challenge as usual PAC learning and target sampling circuit as SAC-RAM. And in this model, a target function is selected according to this given circuit, and these samples are generated according to a target function and unknown example distribution. And the task is to find good prediction. So if we consider this learning model, then the hardness corresponds to auxiliary input one-way function. This is our first result. But important question remains. What is the exact cryptographic notion corresponding to the hardness of usual PAC learning model? Our second result is to give answer to this question by a variant of heating set generator. So now I explain this part. A heating set generator is a weak variant of a pseudo-random generator satisfying this condition. For any polynomial time computable adversary, if the adversary accepts a large fraction of input, then this adversary also accepts at least one pseudo-random string generated by this generator Z. This is a usual heating set generator, but for our result, we need several modifications, especially a weakening step and a strengthening step. And as a weakening step, we add auxiliary input to this generator as previous work. Then interestingly, our generator, auxiliary input heating set generator, becomes a weaker notion than the hardness of learning. Then we add several conditions, especially conditions on arbitrary polystorage and local computability, and we call such a generator as auxiliary input local heating set generator, and we can show that this generator corresponds to the hardness of learning. And this is first, so as we know, this is the first cryptographic characterization for hardness of usual PAC learning model. So our result gives a new seamless relationship between learning theory and cryptography, and this enables us to apply techniques in one field, even in the other field. For example, from cryptography to learning, if we apply cryptographic technique, we can show the following corollary. In PAC learning circuits with target sampling circuit, membership query does not help at all. And we can show this result unconditionally. And it seems to be hard to show this result by only learning theoretical techniques at present. And in the original paper, we also considered the other direction from learning to cryptography. Okay, now let's move on to the second topic. But sorry, due to the time limitation, I explained this part very briefly. So in computational learning theory, one desirable goal is to find a concept class existing in the boundary between easy-to-learn case and hard-to-learn case, because such a class must be the most expressive one in easy-to-learn classes. But this goal, at present, this goal seems to be far. So in this work, we review this goal from meta perspective, that especially where the difficulty comes from. And in this work, we focus on the hardness of determining efficient learnability. And we try to consider this kind of problem. The input is a concept class represented as an evaluation circuit, and the task is to determine the given evaluation circuit whether a given evaluation circuit is polynomial learnable or not. But to formulate this problem, there is a technical issue that usually polynomial learnability is a symptotic notion for sufficiently large polynomial-sized resources. So we cannot get such a formulation directly. To overcome this, our approach is to consider asymptotic complexity. And what we did is first define a language learnable. And this learnable is indexed by two polynomials. And these polynomials represent the upper bound on the size of resources. And we consider the asymptotic complexity of this problem, especially for sufficiently large polynomials. And by the formal definition of this language in the original paper, we can easily show the upper bound in the polynomial hierarchy. But what we want to know is the lower bound, especially for sufficiently large polynomials, whether this problem can be solved in polynomial time or not. And we define the notion hardness of Meta-PAC learning as a situation where this problem does not converge in the class P for sufficiently large polynomials. And we show that this hardness of Meta-PAC learning is indeed equivalent to the hardness of non-uniform PAC learning. In other words, our formulation of difficulty of Meta-PAC learning determining learnability comes from the difficulty of learning itself. This is our third result. Okay, now I explain proof techniques. Indeed, the final result on Meta-PAC learning is shown by very standard techniques, couple reduction and Occam's razor, so I skip this part in this talk. And for results on auxiliary input cryptography, we use a relatively new characterization for PAC learnability given by Dan called RRHS refutation. And this notion was originally introduced to show the hardness of learning from hardness of random CSP, but we use this notion to give a general framework for translating the hardness of learning into auxiliary input cryptography. Especially, first we translate the hardness of learning into hardness of refuting by using the previous technique. Then we translate, by adding several universal circuits, we translate this hardness into secure auxiliary input primitives. And if we apply this framework to our model, PAC learning with target sampling circuit, then we have a secure auxiliary input version of pseudo-random generator. And in fact, this existence is equivalent to the existence of auxiliary one-way function. So we have the theorem. And if we apply this framework to usual PAC learning model, then we have a secure auxiliary input local heating set generator. Okay. In conclusion, in this work, we consider the exact meaning of hardness of learning, and we introduce several notions, and we show the equivalent relationships between them and previous notions. And we give new insights into computational learning theory from several perspectives. This is the end of my presentation. Thank you for watching.